Hello, I am Ryan Campbell, a math graduate student at Emporia State University. For my master's seminar, I have studied enormous numbers. The catalyst for this topic is a challenge that has been circling around the community of players of the trading card game Magic the Gathering. The challenge is based on maximizing the amount of damage that a player can deal on turn 1. Players have been workshopping card combinations and calculating large amounts of damage, and then posting the list of their cards online. Now, normally a player would need to inflict 20 damage to their opponent, but the combos that these players describe inflict massive amounts of damage. We're going to be starting with a quick explanation of the game so that we can understand how large numbers come into play. Then we will talk about immensely large numbers. Some of these topics you may have seen before, such as scientific notation, and we will finalize our presentation today with bringing Magic the Gathering back in as we talk about and compare the large numbers to the amounts of damage that some players have dealt with their Magic the Gathering decks. So, Magic the Gathering, which is also called Magic or MTG, is the original trading card game. It was originally created in order for players at gaming conventions to have something to do on their downtime in between some of the larger games. But it took off, and since the early 90s, there have been tons of players around the world who have been playing Magic. In this two-player turn-based strategy game, a player utilizes resource cards called mana to play for special spell cards that they want to cast. These spells include creature cards that attack the other player, spells that directly deal damage to the other player, utility spells that gain you more mana or allow you to perform more actions, and a large variety of other cards. The goal of the game is to deal 20 damage to the opponent using spells, permanent abilities, and attacking creature cards. Players have found many combinations of cards that create infinite loops to deal infinite damage to the other player. Now, it is not that difficult to accomplish infinite damage. You can regularly see players on a Friday night at a card store dealing infinite damage to an opponent. So, since that is not very interesting, the challenge then requires players to create a 60-card vintage legal deck that deals as much finite damage as possible in the first turn. The opposing player is not actually allowed to do anything in this challenge. So if they have cards in their hand that can affect the game, we just pretend that they don't exist. In addition, if a player in this challenge were to come up with an infinite combination to deal infinite damage, the player could not choose to stop dealing damage to the other player. So you're not allowed to stop your own combination. It just is supposed to play out how it does. So we're looking for finite damage, not just stopping at 20 damage. So the players that have created these decks and posted them online have really just delivered. They came up with so much damage that standard numbers really can't express the amount. So let's go ahead and get into some giant numbers. Okay, right after I chose my topic, several friends asked me about the topic of my seminar. I'm pretty sure they were just being polite, but they should know better than to ask me, a math teacher, about cool new math. So when they asked, I responded, big numbers. So they said, what, like a trillion? No, like really big numbers, I said. So my science major friend offered Avogadro's number. That is way too small, I replied. And they really started thinking here. they answered a Googleplex, and then their grand finale, a Googleplex plus 1. This literally descended into the argument of, well, I could always add 1, or add 2, or I could multiply by 7, or we could take exponents. So a Googleplex squared, or a Googleplex to the Googleplex power. So they even got into exponentiation. In fact, my friends had just stumbled upon Googology, which is the study of immense numbers. And Googology itself has several notations that can help us write these gigantic numbers. We're going to start off with good old scientific notation. It can take care of things like Avogadro's number, which has 20 zeros in it. Scientific notation also neatly writes a googol. A googol is known as 10 to the 100th power, or a 1 followed by 100 zeros. Now, a googol has 100 zeros in it. Typing 20 zeros was more than enough, so typing in 100 zeros for a googol was really more than I was wanting to do. It wouldn't fit neatly into that box. Enter a Googleplex. A Googleplex is 10 to the Google power. So we would get 1 followed by a Google zeros. I didn't want to type in 100 zeros for the exponent, much less type a Googleplex, a Google zeros. So we can see that scientific notation falls short for a Googleplex, which means we need another way to write numbers that are just gigantic. In fact, scientific notation falls miserably short for not only Googleplex, but for the numbers in our challenge. Enter Donald Knuth and up arrow notation. So anyone at Emporia State University's math program has used Knuth's work, probably without knowing his name. Donald Knuth worked to create the typesetting system TeX, aka LaTeX, which I used to typeset this presentation. And a lot of our homework assignments have actually been using LaTeX on Overleaf. So it's kind of fitting that I kind of created this slight homage to Knuth and his up arrow notation in LaTeX. So for large numbers, Knuth created up arrow notation to write more concisely. And up arrows are exactly what they sound like. It's a small arrow that is pointed up. Okay, on the left, we see A and then an arrow pointing up with what looks like an N power of B. What this means is that we have N arrows between the number A and B. Now, I'm going to start with the middle portion of this. It says 1 if N is greater than or equal to 1 and B is 0. So if we have at least one arrow and B is 0, then we end up getting just 1 as our answer. And we can see why here in a second. In the top portion of our piecewise function, we see that we get a to the b power if n equals 1. Okay, so if we only have one arrow, a up b is a to the b power. Now, of course, if b is 0, that would be like saying a to the 0 power, and we all know that that's just 1. Okay, so most of the time we'll be using the a to the b power up from the top part of our piecewise function, or the third piece of our piecewise function, where we end up breaking up these n arrows. Okay, because we can only start evaluating once we get one arrow. Okay, so if we have n arrows, we need to do n iterations. So in this third piece of the function, we end up cascading based on the number of arrows and the size of b. We can see that we reduce the number of arrows by 1. And then over here, we reduce B by 1, but keep the same number of arrows here. Then we would need to evaluate inside the parentheses. So that A with n arrows of B minus 1, we would end up keeping the A and the n minus 1 arrows, and then subtracting 1 more from B minus 1. So we continue this until we end up at just 1 arrow and just B equals 1. Let's go ahead and do some examples so that this can really sink in. Every time we see an arrow, I'm going to just say the word up instead of up arrow, just to save some time. So we've got 2 up 3 equals 2 to the 3rd power, which is 8. Okay, that follows the first piece of our piecewise function. Next, we have 2 up 3. And that reduces, using the third part of our piecewise function, to 2 up, parentheses, 2 up 2. And we can even continue. Since we still have 2 arrows, we have to keep going. Then we get 2 up, 2 up, 2 up, 1. And just like when we do order of operations, we start with the innermost parentheses and work our way out. So 2 to the 1st power is just 2. So inside the parentheses now, we have 2 up 2, which is 2 to the 2nd power. 2 to the 2nd power is 4. So 2 up 4 is 2 to the 4th power, which is 16. Now, these numbers don't sound that fantastic or immensely large, but we're about to blow your mind. Okay, let's get a third arrow on here. We have 2 up 3. And as we continue on, we get 2 up 2 up 2. Again, subtracting 1 arrow on the left and subtracting 1 from that 3 on the right. Okay. If we continue out in the parentheses, subtracting from the 2, right, which is B in this case, we end up getting 1 very quickly. So we can actually be done with the cascading effect that we get there. So we can reduce the inside of the parentheses to 2 up 2. Okay. And 2 up 2 is 2 to the 2nd power, which is 4. Okay, 2 up 4, we use that third piece of the piecewise function, and we get 2 up 3, which I have changed to red. And that's because we have already calculated 2 up 3, which is 16. Okay, so some of these up arrow notation pieces, not only are they recursive, they end up referring back to previous problems. Okay, 2 up 3 is 16. So we get 2 to the 16th power, which is 65,536. I know I promised I was going to blow your mind here, but, 65,000 got a lot bigger than from 8 to 16. Let's make our numbers even bigger.